the lecture is relatively brief. And for the remainder after that, I'm going to have you, there's an activity like usual, but then there was also an activity at the end of last class. If you didn't have a chance to look at it yet, there should be time to look at it today in addition to today's. Okay, so we are going to talk about finding the zeros of a polynomial function. So when you're finding zeros, what kind of numbers can you get? Okay, so if you have a function in completely factored form where all the factors are linear, right? That means that the power on x is 1, or the factors look like mx plus b. Okay. So here's a polynomial in completely factored form. I want to find all the zeros of this function and classify each one as real, non-real, imaginary, complex imaginary, rational, or irrational. So this is some vocabulary that we have been using, but not recently and not that regularly. Okay. So first, let's just find all the zeros. -3, right? Because x plus 3 is a factor, which means x equals -3 is a 0. And then what else is a 0? 1/2, because 2x minus 1 is a factor. You set that equal to 0 and solve, and you get x equals 1/2. And then negative radical 2, radical 2. Yeah. 4 plus 5i, and 4 minus 5i. So these are all different kinds of numbers. Okay, so I'm just going to classify each of them as a type that we have talked about. So which of these numbers are real numbers? And yeah, and the radical 2's, plus or minus radical 2. Those are all real numbers, okay? Which differs from non-real because they don't have any i's in them. Okay? So this would be real, 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 and real. And then these two, they have i's in them, so we would call these non-real. They have an imaginary part, so we call them non-real. That's a good question. An imaginary number is a number that is just has the imaginary part, like 3i would be an imaginary number. Yes. So 4 plus 5i has a real part and an imaginary part. So it's a complex imaginary, is what we call it, as opposed to strictly imaginary. All right. So of the real numbers, of just the real numbers, so ignore the non-reals for a few minutes, of just the real numbers, some of these are rational and some are irrational. So which of them are rational? The first two. Rational means you can write it as a fraction, right? The root of the word rational is ratio. If you can write it as a fraction, it's rational. So -3 could be written as a fraction as -3/1. 1/2 is already written as a fraction, so this is rational. But then square roots, if it's not a perfect square underneath the radical, those are irrational numbers. Yeah. Yes, they are crazy, messed up decimals. That's a good description. Okay. So your first classification of any number is real or non-real, right? And then if it's real, it can either be rational or irrational. If it's non-real, it can either be imaginary or complex imaginary, right? So strictly imaginary, just a term with an I, or complex imaginary, which means it has a real part and an imaginary part. So both of these are complex imaginary. What is the degree of this polynomial? How do you get 7? If you count up the number of linear factors, so x plus 3 is squared, which means x plus 3 is a factor twice, right? So you go 1, 2, 3, 4, 5, 6, 7. Yeah. And the reason that that works, that you can just count the factors, is because you just imagine if you were going to multiply all these together, it would take forever. But you don't have to actually multiply them together to figure out what the highest power on x would be. This first factor here, x plus 3 squared, it's going to have an x squared. Then you're going to have to multiply it by a 2x, an x, an x, an x, and an x, and you'll get an x to the 7th. So my degree here is 7. How many linear factors does the polynomial have? Even if you count it twice, how many are there? 7. Yeah. Yep. 1, 2, 3, 4, 5, 6, 7. Coincidence? Degree equals the number of linear factors? Doubtful. Yeah. How many zeros does this polynomial have? If you count a multiplicity 2 as 2 separate zeros. 7. Yeah. So -3 is a 0, right? If I just count the ones I listed here, I've got 1, 2, 3, 4, 5, 6. But the -3 is a multiplicity 2. If I count that twice, I get 7. Right? Again, coincidence that the degree matches the number of linear factors, matches the number of zeros? No, not a coincidence. Okay, so here's a polynomial function, x cubed plus x squared minus 5x minus 2. We're going to find the exact values of all the zeros of this polynomial, meaning if it has square roots in it, leave the square roots, don't get a decimal. That's what it means by exact. And then once I have all the zeros, I'll know all the factors and I can write it in completely factored form. All right, so to find the zeros of a polynomial, or any function, to find its zeros, you set the function equal to 0 and try to solve it. Why? How does that do? What am I? Yeah, and zeros are like x-intercepts. So basically I've made the y a 0, right? Solving for the x. What x's will make the function 0? That's why they're called zeros. Yeah. Okay, so what I need to be able to do to solve this equation is factor it, right? But it's a cubic and I don't have any techniques for factoring a cubic. So I'm going to use my graphing calculator to find, just cross my fingers. I really, really hope that there's one nice integer 0. So I graph it, and I'm not going to bother because I have the picture right here. Right, so I graph it, and I say, oh, look, it goes through the x-axis perfectly at x equals 2. So I have a 0 at x equals 2. So now that I have a 0 of the polynomial, I also have a factor, 2 for the price of 1, right? What's the factor? X minus 2. Okay. Now I can use polynomial division to find another factor. So I'm going to write out my polynomial, x cubed plus x squared plus 5x minus 5x minus 5x minus 2 divided by x minus 2. Why don't you guys take a few minutes and see if you can remember how to do this? Looks like you guys really learned this. This is very exciting. All right, so you start by just looking at the leading terms, the x and the x cubed, and you can ask yourself the question one of two ways. You could just say x cubed divided by x, divide the leading terms, or alternatively say, what should I multiply x by to make an x cubed? X squared, and we line that up over the x squared term in the dividend. Then, just like with division of real numbers, you take your x squared and you're going to multiply it by the divisor. Multiply x squared times x and -2. You got to distribute it. So we get x cubed minus 2x squared, and then I have to subtract the whole thing. All right, so x cubed minus x cubed goes away. X squared minus -2x squared is 3x squared. Bring down the minus 5x. Okay, Now again, now you just start over. Look at the leading terms. X and 3x squared. What do you multiply x by to make 3x squared? Positive 3x. 3x times x is 3x squared. 3x times negative 2 is negative 6x. And we subtract. So 3x squared minus 3x squared, those cancel. Negative 5x minus negative 6x is x. Bring down the minus 2. What do you multiply x by to make an x? 1. 1 times x minus 2 is x minus 2. Subtract, and I get 0. If I didn't get 0, I would know I did it wrong, because I know x minus 2 is a factor, because x equals 2 is a 0. Yeah, unless I made a typo in my graph or something. All right, so I now have another factor, and I forgot to ask you before we started, what degree do you think it will have? 2, because if you have an x minus 2, and you're going to multiply by something and get x cubed, it has to be an x squared. Yep. All right, so now we can write f of x as the product of two factors. F of x is x plus 2 times x squared plus 3x plus 1. X minus 2. Yeah, thank you. All right, but then remember what our goal was from part A. I had set the function equal to 0, trying to find the zeros. So I had x cubed plus x squared minus 5x minus 2 equals 0. And now I have successfully factored f of x. So I've got x minus 2 times x squared plus 3x plus 1 equals 0. And I can set each factor to 0 and solve it. So x minus 2 equals 0, or x squared plus 3x plus 1 equals 0. This one gives me that x equals 2, and I already knew that, right, from the graphical one. But there's one of my zeros. How do I solve this thing? Yeah, factor it or use the quadratic formula. It doesn't factor, so I use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So this simplifies to x equals negative 3 plus or minus radical 5 over 2. So there are my other two zeros. So I've now found my 3 zeros. 2, the x equals 2 I found graphically, and I found the other 2 by doing long division, taking the resulting quadratic, and using the quadratic formula. So now that we've finished finding all the zeros, we could write f of x in its completely factored form. So remember, the 3 zeros are x equals 2, negative 3 plus radical 5 over 2, and negative 3 minus radical 5 over 2. So I have my 3 zeros, which means I can write f of x as the product of 3 factors, and each factor looks like x minus one of my zeros. So x minus 2, I already had that one. But then this quadratic now factors to x minus and x minus, right? So it's going to be x minus something. If that thing is negative, then it's x plus, but I'm just going to leave it as negative root, which is not root 3, it's just negative 3. There we go. Negative 3 plus radical 5 over 2, and negative 3 minus radical 5 over 2. All right, so what's the degree of this polynomial? 3. At the beginning, it was all multiplied out, and it was at x cubed. How many linear factors does it have? 3. How many zeros does it have? 3. Good. All right, so this, the two examples that we just did, leads us to some conclusions. Conclusion 1. If a polynomial function has degree n, then if you count multiple roots separately, the equation has exactly n complex zeros, meaning if you count real and non-real zeros. It will have degree n will have n zeros. An nth degree polynomial, if you have degree n, it can be expressed as the product of n linear factors and also maybe a non-zero constant, where each linear factor is of the form x minus one of the zeros. Irrational zeros and imaginary zeros both occur in pairs. We call them conjugate pairs. A plus bi, its conjugate pair is a minus bi. So they'll occur in pairs, like in my first example up here. I had 4 plus 5i and 4 minus 5i. They come together. It is, exactly. Yeah, when you're doing the quadratic formula, you're going to have the plus or minus, and you always will come out in pairs. And that's the same reason that your irrational zeros also occur in pairs. So for example, if 1 plus radical 2 is a 0, then so is 1 minus radical 2. And that happened in this previous example. We got negative 3 plus radical 5 over 2 and negative 3 minus radical 5 over 2. Same thing, the quadratic formula with its plus or minus always will make that happen. So those are our 4 conclusions about polynomials. These first 2 together are called the fundamental theorem of algebra. They're that important. I'm not going to test you on the name of them. You just need to know what they say. All right, so let's look at number 4. We want to find a third degree polynomial function. Has to have real coefficients, so you don't want to have any imaginary numbers when you're done. It has negative 3 as a 0 and I as a 0, and f of 1 equals 8. And we're going to write it out in factored form as a product of linear factors, and standard polynomial form, we'll multiply it all together. Okay, so if it's a third degree polynomial, how many zeros should it have? 3. How many did I give you? I gave you a hint. What is it? The I. If I is a 0, what else has to be a 0? Negative I. Think of that I as 0 plus I. Its conjugate is 0 minus I. Has to also be a 0, right? And then negative 3, right? So if I is a 0, also negative I. So my zeros I can list as x equals negative 3, I, and negative I. And so I have degree 3, I should have 3 zeros, and I should have 3 factors. X plus 3, right? X minus I, and x plus I. 3 factors. But part A here says that I can express it as the product of n linear factors and maybe a non-zero constant, right? I might have a non-zero constant in front here, A. So it's got to be that f of x is equal to some non-zero constant times x plus 3 times x minus I times x plus I. Now, why can I put a constant there? What does that A do in terms of transformation, transforming the function? It's going to change. It's going to determine the n behavior, right? In this case, it's a cubic, so it's either going to tell me right arm up, left arm down, or left arm up, right arm down, right? What does it tell me in terms of being an outside change, multiplying the function by something? What does that do to the graph? I can multiply the outside by a constant. Vertical stretch. Yes, it's a vertical stretch. And a vertical stretch won't change the location of your zeros, right? Because when you zeros mean the y coordinate is 0. When you multiply 0 by something, it stays where it is. Okay, so A vertical stretch won't change the location of zeros. So for example, I could have, a cubic that looks like this, or a vertically stretched version of that, same zeros, right? So just because I have these zeros doesn't mean that I know everything about the function. There's some leading coefficient that tells me how tall or short this guy is. How can I figure out what that coefficient is? Is there a piece of information that I was given that I haven't used yet? F of 1 equals 8. So that tells me if I plug a 1 in for x, I should get an 8. So let's go ahead and do that. F of 1, I don't know, is 1 plus 3 times 1 minus I times 1 plus I. And that should equal 8. So I just plugged a 1 in for x, and I should get an 8. So let's go ahead and simplify multiplying these three factors. Well, 1 plus 3 is 4, right? 1 minus I times 1 plus I. You guys remember how to multiply imaginary numbers? Get some 1 squared, I squared. I squared is -1. Yeah, I squared was -1. So first we're just going to FOIL these out. Okay, so 1 times 1 is 1. Plus I and minus I cancel. And then I get minus I squared. I'll just leave it like that for now. And then over here, I'll write, remember, because I'm sure you do, because I taught you and you never forget the things I tell you, right? I squared equals -1. That was the definition of I, and we learned it like way back in the semester. So I'm going to replace that I squared with a -1. So this says I minus -1, sorry, 1 minus -1, which is 1 plus 1, which is 2. So A is 1. So now I have my formula. My final formula in factored form is this guy, but replace the A with a 1. Well, yeah, you don't have to write anything. Yeah, because multiplying by 1 doesn't do anything. So let's write that out on a new page. 1 times x plus 3, x minus I, x plus I. X plus 3, right? Yeah, okay. All right, so like Katrina said, we don't actually have to write the 1 there. I just did it so that when you go back and read these, you'll see that I replaced the A with that value. Okay, so this is my factored form. Done with that part. But they asked me to also give this in the standard polynomial format, that like ax cubed plus bx squared plus cx plus d. To get that, I have to multiply it all together. All right, so I have f of x equals x plus 3 times, I'm going to multiply these guys together first. I think it's going to be easiest if I deal with the complex numbers first. X squared minus I squared. Yeah. X squared. So first, x squared plus ix minus ix, those cancel, and then minus I squared. But I squared is really -1, so this says x squared minus -1, which is x squared plus 1. This is a -1. All right, now I can FOIL my x plus 3 and my x squared plus 1. First, I get x cubed. Outer, I get x. Inner, I get 3x squared. And last, plus 3. Yes, I'm just going to reverse the two middle terms because we typically write these in descending powers of x. So there's my function that has zeros at -3, I, and -I, and passes through the point 1, 8. Let's check that it satisfies all the conditions that it was supposed to. I'll use my graphing calculator. All right, so in y equals, I'm going to put this function that I just found, x cubed plus 3x squared plus x plus 3. And I guess I'll just do zoom 6. All right, it does look like it has an x-intercept at -3. But my other zeros are at I and -I. Where are those on here? Why not? I is imaginary. Yeah, when you have imaginary zeros, they don't show up on they don't show up on the graph of the function if your zeros are imaginary. So x-intercepts show up, or your real zeros show up as x-intercepts. Your imaginary zeros are imaginary. Yeah, they show up as nothing. But does this guy go through the point 1, 8? F of 1 equal 8? Let's check the table. If I put in a 1, I do get 8. And I think I don't know if I've ever tried this, but your calculator has an I button, and I is supposed to be a 0. So if I plug in an I, I'm supposed to get 0, right? Type in an I. It won't let me do it. Figures. Let's try it from the home screen. Y1 of I. It won't let me do that either. But what if I just type it? What if I just do I cubed plus 3 times I squared plus I plus 3? Lets me do that. I get 0. And I should get 0, right? Because I is supposed to be a 0 of this function. And then I'm going to do it again, but I'm going to type in -I this time. I is in a second function above the decimal point. So we can do -I cubed plus 3 times -I squared plus -I plus 3 also gives 0. You can do that in your head too, right? Because we know all the powers of I. Let's do that. F of I would be I cubed plus 3I squared plus I plus 3. Okay, so I cubed, anybody remember how to simplify I cubed? I cubed. No. Oh, that's something different. If it's odd, don't modify. That was to remember square roots, right? Even in odd roots. Well, to get I cubed, I could multiply I squared and I together, which would be -1 times I, which is -I. Good. To get I to the 4th, I could multiply an I squared times an I squared. Yeah. -1 times -1 is +1. I to the 5th. To get an I to the 5th, I would do an I to the 4th times an I to the 1st. All right, what's I to the 4th? 1. Yeah, we figured it out a minute ago. And so 1 times I is I. Back to the beginning. I to the 6th, right? I could take my I to the 5th times I, And then I would have I times I, which is I squared, which is -1, back to here. So it repeats every 4, yeah. So I cubed is -I. I squared is -1, so this is -3, plus I plus 3. -I and a positive I cancel, a -3 and a positive 3 cancel, and I get 0. So even though you can't see I and -I in the x-intercepts, you can still check that they're zeros of your polynomial by plugging them in.